Radioactive well logging is a method of studying the materials surrounding exploratory boreholes, a tool consisting of a neutron or gamma ray source and one or more detectors is lowered into the borehole. The response of the detectors to radiation returning from outside the borehole depends in part on the lithology, porosity and fluid characteristics of the material. In principle, the characteristics of the materials outside the borehole can be inferred from the response of the detectors. Any activity that produces or uses radioactive materials generates radioactive waste. Mining, nuclear power generation and various processes in industry, defense, medicine and scientific research produce byproducts that include radioactive waste. Radioactive waste can be in gas, liquid or solid form, and its level of radioactivity can vary. The waste can remain radioactive for a few hours or several months or even hundreds of thousands of years. Because it can be so hazardous and can remain radioactive for so long, finding suitable disposal facilities for radioactive waste is difficult. This focus of this chapter is on the following topics, including introduction to radioactive well logging, methods used in radioactive well logging, introduction to nuclear waste management, nuclear waste disposal methods. Well logging is a technique for obtaining geological information about subsurface rocks by obtaining rock samples from the well and or by using remote sensing devices. Cores and well cuttings are actual samples of the subsurface rock materials. Devices have been developed that can test the rocks of the well hole for their electrical properties, acoustic properties, radioactive properties, hydrocarbon contents, etc. Logs are made as a record of the well hole. A device is lowered the length of the well hole and the characteristics are recorded on a continuous graph known as the log sheet. Radioactive well logging is a method of studying the materials surrounding exploratory boreholes, a tool consisting of a neutron or gamma ray source and one or more detectors is lowered into the borehole. The response of the detectors to radiation returning from outside the borehole depends in part on the lithology, porosity and fluid characteristics of the material. In principle, the characteristics of the materials outside the borehole can be inferred from the response of the detectors. There are 5 main nuclear well logging tools. The density porosity tool using cesium-137, the neutron porosity and elemental analysis tools typically using americium beryllium, that is AMBE, radioisotope sources, and the neutron absorption and carbon oxygen, that is CO tools, which use 1 mega electron volt neutrons from deuterium tritium, that is DT accelerators. The nuclear tools of primary interest use either sources of gamma rays or neutrons. The one exception to this is the neutral gamma ray tool, which has no source at detectors the neutral gamma rays that are present in the rock formation outside the borehole. There are 5 main nuclear well logging tools: the density porosity tool using cesium-137, the neutron porosity and elemental analysis tools typically using americium beryllium, that is AMBE radioisotope sources, and the neutron absorption and carbon oxygen, that is CO tools, which use 1 mega electron volt neutrons from deuterium tritium, that is DT accelerators. Gamma ray logs. Gamma ray logs reflect naturally occurring radiation in rocks penetrated by the borehole. Although several types of rays are emitted, only gamma rays have enough penetration to be practical use in logging the natural radioactivity of the rocks. All natural rocks contain some radioactive material. However, compared to that of the uranium or radium ore, even of low grade, the radioactivity of most rocks is very small. The radioactivity of a rock is usually expressed in terms of equivalent amount of radium per gram of rock required to produce the same gamma ray intensity. Although there is no fixed rule regarding the amount of radioactivity a given rock may have because of potassium decay, shale, clays and marls are generally several times more radioactive than clean sands, sandstones, limestones and dolomites. Because shale, clays and marls have radioactivity that are of the same order, the term shale is used in this article to generally denote any of these three formations. Similarly, for the sake of generalization, the term sand is used to denote sands, sandstones, limestones and dolomites, since these four rocks have radioactivity of the same order. The radioactivity of clean sands, that is sands free of shale materials, shale, clay, marl, is generally very low. Sands that contain some shale material have a somewhat higher radioactivity, and the increase is proportional to the amount of shale contained. Therefore, shale sands and sandy shale generally have a radioactivity that is between that of clean sands and that of shale. In a given area, the radioactivity of shale does not generally vary too much, so that a gamma ray log is an approximate measurement of the quantity of shale contained in a formation. Marine sandstones with uranium, however, have high radioactivity. The radioactivity of shale varies from area to area. In the tertiary and more recent formations, that is, those usually found in the Gulf Coast and in California, the radioactivity of the sediments as a whole is generally several times weaker than in the older rocks found in other petroleum provinces. Some organic marine shale has a much higher radioactivity than the ordinary shale in the same area. However, they are generally relatively thin and are not found too frequently. If present, marine shale makes excellent geological markers. Gamma ray logs have been used to distinguish some uranium producing horizons in sedimentary rocks from the western United States. In more recent years, gamma ray logging has been used to distinguish different freshwater aquifers separated by clay shale in alluvial aquifers in sedimentary bedrock, confined artesian type aquifers. The drop in the gamma radiation shows the transition from clays to sand and gravels. Interpretation of gamma ray logs. The interpretation of gamma ray logs can be summarized as follows. Number 1. In a given area, only the relative radioactivity of the various rocks is of significance. Number 2. Rocks of low radioactivity include primarily clean sands, sandstones, limestones and dolomites. Anhydrite, salt, lignite and coal have also a low radioactivity. Their radioactivity increases when they are shale. Number 3. Ordinary shale has a much higher radioactivity than the rocks listed above. The radioactivity of sandy shale is less than that of shale. Shales are sufficiently high in radioactivity and can generally be easily distinguished from the other rocks on a gamma ray log. Application of gamma ray logs. Gamma ray logs are used in the following instances, including number 1, to log cased holes. No electric log can be obtained in cased holes. Number 2, to log dry holes. no electric log can be obtained in holes that do not contain water or mud. Number 3, to log holes containing salt water or salty mud, the electrical logs obtained in such holes are generally poor. Number 4, to supplement the information given by the electric log, that is identification of formations, estimating the amount of clays and sands, etc. Number 5, to locate radioactive ores, uranium in particular. Number 6, to help locate lignite and coal beds. Number 7, to help locate clay and fresh water sands. Coming to the neutron logs. Neutron logs record the response of formations to neutron bombardment induced artificially. A neutron source is lowered into the wellhole. Porous units absorb more neutrons and return or reflect fewer neutrons. Denser rock units reflect more neutrons and yield higher neutron radiation values. Porous sandstones usually have low neutron values. There are 4 main neutron source logging tools, including number 1, the neutron moderation tool, which primarily measures hydrogen content that can be related indirectly to porosity. Number 2, the carbon oxygen or CO tool, which measures the ratio of carbon to oxygen, which can be indirectly related to oil and or water content. Number 3, the formation neutron cross section tool, which measures the neutron absorption cross section in both the borehole and the formation outside the borehole. And number 4, the mineral or elemental analysis logs, which measures parameters from which the chemical and mineral composition can be inferred. Coming to the bulk density logs. Bulk density logs, sometimes called density log or DENSI log, record induced radiation from wellhole. A skid mounted device lowered into the wellhole emits medium energy electrons and measures returning gamma ray values. Gamma rays are generated by electron collisions with atoms within the rock formations. The gamma ray return values that are related to rock density, and most bulk density values on the log graphs are recorded as grams per centimeter cube. Any activity that produces or uses radioactive materials generates radioactive waste. Mining, nuclear power generation, and various processes in industry, defense, medicine, and scientific research produce byproducts that include radioactive waste. Radioactive waste can be in gas, liquid, or solid form, and its level of radioactivity can vary. The waste can remain radioactive for a few hours or several months or even hundreds of thousands of years. Because it can be so hazardous and can remain radioactive for so long, finding suitable disposal facilities for radioactive waste is difficult. Depending on the type of waste disposed, the disposal facility may need to contain radiation for a very long time. Proper disposal is essential to ensure protection of the health and safety of the public and quality of the environment, including air, soil, and water supplies. Radioactive waste disposal practices have changed substantially over the last 20 years. Evolving environmental protection considerations have provided the impetus to improve disposal technologies and, in some cases, cleanup facilities that are no longer in use. Designs for new disposal facilities and disposal methods must meet environmental protection and pollution prevention standards that are stricter than were foreseen at the beginning of the atomic age. Disposal of the radioactive waste is a complex issue, not only because of the nature of the waste, but also because of the complicated regulatory structures for dealing with radioactive waste. There are a variety of stakeholders affected, and there are number of regulatory entities involved. Types of radioactive waste. According to the amount and type of radioactivity in them, nuclear waste materials can generally be classified as exempt waste and very low level waste. Exempt waste and very low level waste, that is VLLW, contains radioactive materials at a level which is not considered harmful to people or the surrounding environment. It consists mainly of demolished materials such as concrete, plaster, bricks, metal, valves, piping, etc., produced during rehabilitation or dismantling operations on nuclear industrial sites. Other industries such as food processing, chemical, steel, etc., also produce VLLW as a result of the concentration of natural radioactivity present in certain minerals used in their manufacturing processes. See also information page on naturally occurring radioactive materials. The waste is therefore disposed of with domestic refuse, although countries such as France are currently developing facilities to store VLLW in specifically designed VLLW disposal facilities. Low-level waste, that is LLW, is generated from hospitals and industry as well as the nuclear fuel cycle. It comprises paper, rags, tools, clothing, filters, etc., which contain small amounts of mostly short-lived radioactivity. It does not require shielding during handling and transport and is suitable for shallow land burial. To reduce its volume, it is often compacted or incinerated before disposal. It comprises some 90% of the volume but only 1% of the radioactivity of all radioactive waste. Coming to intermediate level waste. Intermediate level waste, that is ILW, contains higher amounts of radioactivity and some requires shielding. It typically comprises resins, chemical sludges and metal fuel cladding as well as contaminated materials from reactor decommissioning. Smaller items and any non-solids may be solidified in concrete or bitumen for disposal. It makes up some 7% of the volume and has 4% of the radioactivity of all rad waste. Coming to the high level waste, that is HLW. High level waste or HLW arises from the burning of uranium fuel in a nuclear reactor. HLW contains the fission products and transuranic elements generated in the reactor core. It is highly radioactive and hot, so requires cooling and shielding. It can be considered as the ash from burning uranium. HLW accounts for over 95% of the total radioactivity produced in the process of electricity generation. There are two distinct kinds of HLW, including used fuel itself and separated waste from reprocessing the used fuel. HLW has both long-lived and short-lived components depending on the length of time it will take for the radioactivity of particular radionuclides to decrease to levels that are considered no longer hazardous for people and the surrounding environment. If generally short-lived fission products can be separated from long-lived actinides, this distinction becomes important in management and disposal of HLW. Nuclear waste comprises a variety of materials requiring different types of management to protect people and the environment. One of the factors in managing nuclear waste is the time that they are likely to remain hazardous. This depends on the kinds of radioactive isotopes in them and particularly the half-life characteristics of each of those isotopes. The half-life is the time it takes for a given radioactive isotope to lose half of its radioactivity. After 4 half-life, the level of radioactivity is 1/16 of the original, and after 8 half-life 1/256th. Nuclear waste disposal methods. The methods of nuclear waste disposal includes the following. Number 1, the short-term storage. Number 2, long-term storage. And number 3, transmutation. Coming to the short-term storage of nuclear waste. Radioactive materials decay in an exponential fashion. Short-term storage will reduce the radioactivity of spent nuclear fuel significantly. 10-year storage can bring 100 times decrease in radioactivity. A further reduction of radioactive emissions similar to that of the first 10 years would take another 100 years of storage. Storing the waste for at least 10 years is recommended. The reduction in radioactivity during short-term storage makes handling and shipment of the waste much easier. After short-term storage, the waste will be sent for transmutation or long-term storage. Number 2, long-term storage for high-level radioactive waste. While there are methods of significantly reducing the amount of high-level radioactive waste, some or all high-level radioactive waste must end its journey in long-term storage, because long-term refers to a period of thousands of years. Security of the radioactive waste must be assured for over geological time periods. The waste must not be allowed to escape to the outside environment by any foreseeable accident, malicious action, or geological activity. This includes accidental uncovering, removal by groups intending to use the radioactive material in a harmful manner, leaching of the waste into the water supply, and exposure from earthquake or other geological activity. In addition, this security must be maintained over a period of time during which not only will the designers of the storage area die, but also the host country will in all likelihood see different political regimes. Posing further difficulty is the fact that some of this waste is plutonium and other actinide elements produced as byproducts of the uranium fission. These elements are not only highly radioactive but highly poisonous as well. The toxicity of plutonium is among the highest of any element known. Areas currently being evaluated for long-term storage and nuclear waste are A. Space, B. Under the seabed, and C. Large stable geologic formation on land. Long-term storage on land seems to be the favorite of most countries. The radioactive material may be vitrified and buried in caverns created in a large rock formation. When use of the storage area is complete, it would be sealed again with stone. While still extremely expensive and considerably unsafe, this is the most viable storage option currently available. Using methods that reduce the amount of radioactive waste could further enhance safety levels, while most countries should not only be able to find suitable or suitably safe sites in stable geological formations, they should also demonstrate this safety so as to create public confidence. This is best achieved where there is simple geology. The nuclear tools play roles in the determination of a number of the most important hydrocarbon well characteristics such as porosity, element, composition, and whether or not oil or water is present. The nuclear tools of primary interest use either sources of gamma rays or neutrons. There are a number of nuclear well logging tools that have been and still are important in the evaluation of hydrocarbon wells and reservoirs. While the recent interest in logging while drilling tools has changed the emphasis somewhat, interest in nuclear tools has remained as high as or higher than ever. Nuclear waste are a significant part of the nuclear power picture and need to be managed and disposed of properly. However, in more than 50 decades of civil nuclear power experience, they have not caused any serious health or environmental problems, nor posed any real risk to people. While most countries should not only be able to find suitably safe sites in stable geological formations, they should also demonstrate this safety so as to create a public confidence. Thank you very much.